It works. All right. Hello, yeah, my name is Mark Asphalt. This is joint work here at the CWI from me, Pedro Holanda, Tim Goodman, and Hans Mielaisen. And in this work, we basically try to look at some common pitfalls that we've encountered when people try to put data management systems against each other. So right now, what's the state of database benchmarking? Well, there's many problems still. In the industry, a lot of people just put white papers online. Oh, sorry?
So I should just put the volume up. Yeah.
Oh,
yeah. I think
in the back of the people.
Deleting the noise here. Wait.
I can.
This won't work.
I can talk like this. Maybe it's better.
Yeah. The thing is.
I'll just hold it like this.
It's not quite the laptop.
No problem. Okay. Yeah, so currently there's many problems. In the industry, many companies, I should say, just put their white papers online with often quite misleading benchmarks, with the basic takeaway: trust us, our product is perfect, we beat everyone, it's great. And in academia, there's a lot of unreproducible numbers in papers with the message, trust me, my own proposal is the very best. And this leads to a sort of paradox where we have a lot of benchmark results being published, but few of them are useful. So why is that the case? Well, everyone kind of needs to have this graph. Either in their paper, they need to have this graph because a paper without this plot will not get accepted, and a product without this plot will not get traction or will not get sold. And this creates a bit of a perverse incentive to basically make this happen. And this can be either by accident or maliciously. People can make this plot happen for their system and the opposing system. So our motivating example for making this work is that we encountered this in a paper accepted in a top conference, where they did a benchmark of TPCH Query 1, and they compared their prototype against a real database system, Hybrid. And we found when we actually looked at their source code, they had hard-coded group counts, a hard-coded hash, they had two small data types to hold the aggregations, so there were accuracy problems, they didn't handle overflows, and surprise, they were faster than the database. But of course, their solution provided incorrect results and would crash if you would change the dataset. So this is not really a fair comparison because you're comparing different features, you're comparing incorrect results against correct results. But in the end, if you just look at the paper, you just see the graph, you just see they're being faster, and you won't really spot this unless you actually do some research behind it. So we made this basically list of common pitfalls in database performance testing that you can use if you want to evaluate whether or not a performance benchmark is fair, or if you're running your own to make sure that you're making a fair comparison. And I'll talk about these four. We have some more in the paper as well. So, of course, the top one that's relevant in all science is non-reproducibility. So the example we gave was quite a bad comparison, but we could at least spot the database crimes, right? The benchmarking crimes, because they published their code. If they would not have published their code, we could have never figured this out. And this happens very often, unfortunately, where people just don't put their code online, just nothing is available. And unfortunately, this also has very little consequence in terms of paper acceptance. We found that a lot of people don't put their code online, and you can never spot these crimes. So they have these benchmark numbers, but there's no way to reproduce them unless you maybe send them an email, but then they might not respond either. They may have closed source code. So there's a very noble effort here, of course, with the sigma reproducibility, but it's completely optional, and many people do not partake. So this is, of course, very bad. And to give you an example of how this can be a bit, how this can be difficult if you don't make your numbers reproducible, you don't put your benchmarking scripts and everything you have used to generate plots online. We've made this experiment. And here we have a sort of Escher-like scheme where we run MariaDB, Postgres, and SQLite on TPCH Query 1. And we use the exact same data and query. And you can see that in the first plot, Postgres is faster than MariaDB. In the second plot, SQLite is faster than Postgres. And in the third plot, MariaDB is fast and SQLite. So we have the exact same query and same data, so you can guess what is the difference between these versions. And there's a bunch of things that can be that you will never figure out unless you have the full benchmark script. So let's see. What is it? Well, you might think, oh, they have different configuration parameters. No, they have the same configuration parameters. You might think, oh, we compiled them with debug and optimized. No, same compilation flags. You might think, no, we used a different database version. No, same database version. The difference is very simple. We use a different schema. And so basically, we use a double instead of a decimal, and this gives 3 times faster performance on this query for MariaDB, because apparently decimals are not that efficiently handled. And you will never figure this out because you're not putting this in your paper. So unless you put your benchmark results online, no one is going to figure out that this is what caused these results, basically. And one thing that this still gives correct results according to the DBTest specification. So it's not like this produced incorrect results either. All right. Well, there's the other things. We've kind of given them away already. The failure to optimize. And if you're making a comparison plot between your system and someone else's system, there's kind of a perverse incentive there. Because you have all the incentive in the world to optimize your own system, and 0 incentive to optimize the competition. And there's many ways in which you can optimize, especially in the database world. You can do different compiler optimizations, which are kind of obvious, but some people don't, some people miss this. If they just run down the source code, they might compile a debug version. There's configuration. And this can have quite an impact on performance for data management systems. And, but unfortunately the fix for this is quite hard because, as we all know, optimizing database is difficult. There's an entire profession dedicated to it. So how do you do it? Well, the fix that we have tried to do, which is difficult, is to involve the competition. So you can send the authors of the paper or of the database system an email and ask them, hey, we're trying to run a benchmark. Can you help us optimize your system for this benchmark? Or you can use the configuration of that they have used in their paper for a similar benchmark. It gives lots of work, but it does create a fair comparison. And here we can see some consequences of the optimization that it can have on the system performance. So we can see that if we change the configuration of Postgres, we get a factor 2 in performance improvement. And with Mongo, if we compile the optimized flags, we get a factor 2 performance improvement as well. So this can all be very relevant. Then of course, a lot of people do apples versus oranges comparison. So they publish their algorithm and they compare a standalone implementation of the algorithm for one query against the full database system. And often there's a feature mismatch there, where their little demo maybe doesn't do correct overflow checking, or it doesn't have to deal with transactions, it doesn't have to do with multiple clients. So there's a lot less that the little prototype has to do, that the full system does have to take care of, which can also lead to some unfair comparisons. And again, the fix for this is difficult, but either you should compare a standalone implementation against another standalone implementation if you want to evaluate your algorithm, or you should integrate your algorithms into a full system and then compare against that full system. Because otherwise you're creating, again, an unfair comparison. So here's where we have a nice example of TinDB. We've seen this a few times in papers as well, where people label their little prototype as a database even though it does none of the things that a database does. And TinDB is a hand-rolled standalone C program that runs query 1. It's not a database, but of course it's very fast because everything is hard-coded. And surprise, it runs faster than a database system. Another one that's a bit more subtle, that may seem obvious, but a lot of people don't actually check for, is incorrect results. And bugs sometimes make code very fast. And maybe you don't scan all the data, you scan half the data, or something goes wrong in your implementation, and it makes your code faster. But this may be invisible in your benchmark. If all you're doing is running a time command on this query, then yeah, it doesn't matter that the bug is there. Your code is faster now. So of course, if you run any sort of performance benchmark, you should always check the results. we have actually, this is something we have run into ourselves, where we ran at our database, our benchmark, and we thought, oh, it's really fast. Wait, it doesn't give the correct results anymore. We're skipping half the data. Yeah, I mean, it's not even timidly compete with this implementation of TPCH query model. It's very, very fast. But yeah, it's also not a good, yeah. And the solution for this is just always check the results in your benchmark script. And if you run with different data sets and benchmarks, because there's also a more subtle way in which you can give an incorrect result, is that you can give a correct result for a certain data set for a query, but if you change the data set, your result is incorrect again, because of overflows or because of your hard coding, group counts, that sort of stuff. And for this, you should run with some well-tested database, maybe even two, and compare the results against them to make sure that you get it right. So the summary is, you should be aware of these pitfalls when you're writing the benchmarks, when you're reviewing benchmarks, and take them into account whenever you see the graph we showed before. And of course, we are by no means immune ourselves. This is not a finger-pointing session. I've also left out any sort of finger-pointing here. I have not mentioned any of the things we have encountered. And we made this little checklist of things you can look out for to help you make some more fair performance comparisons between database systems. Thank you very much.
Excellent. Questions?
This is very interesting to see. Compare the benchmark numbers and see how good they are, and all these checklists, and hopefully somebody can help me if one day I'm going to go through the checklist. I don't want to go through manually. Is there any thinking going further, like say, what can we do to really automate the checking of the checklist? What can we do to really actually reduce this kind of pitfalls?
Well, certain things of this could be automated by having some sort of benchmark suite. For example, checking if the results are correct. You can do automatically. You can collect several results automatically. You can differentiate between cold warm, hot runs automatically as well using the benchmark suite. But certain things are very challenging to do. Obviously, like you cannot take a standalone algorithm and automatically implement it into a database system. That's something that in the end you have to do yourself. So it's certain things of this can certainly be optimized. You can automate, but not all, unfortunately. It's fair benchmarking is a difficult problem, which is why very few fair benchmarks happen.
Thanks. Yeah, looking forward for any further effort. Thanks.
Thanks very much. It's wonderful to see this sort of thing being made visible. But I wonder if we could actually go to the source of the problem. The source of the problem is that desire to have a graph which shows your system better than somebody else's. You know, I just wonder what you would think about trying to change the culture so that people provide benchmarks not to show that their system is better than another, but rather to show where their system does well and where it does bad.
Yeah.
Stonebreaker famously once said, you know, if a collection of data doesn't show a crossover point, you shouldn't be showing a collection of data. You should instead give an argument why it's always better. Otherwise, what you want data for is to identify the trade-offs. I was wondering if we could change culture that way.
Well, that would be, of course, great, but very, very difficult. Especially because it's not just academia, it's also industry. And they have even less of an incentive because we are scientists. We, in the end, want to share knowledge, but they want to make money, and make money off of being fast. So it's very difficult, but would be great.
Great talk, thanks. So what do you recommend to benchmark developers? So what tools should be included in a benchmark like TPC or the DBC benchmarks to make this more sure that people will actually do these steps?
Well, you can take a look at this checklist and put some of them in. The problem is also for benchmark developers, it's difficult because of course you have the TPCH benchmark. And a a lot of these rules are actually in there. For example, there is like, you cannot, you should not do benchmark-specific optimizations. That's in the TPCH standard. People don't follow this, of course. So even if you develop a benchmark that has all the right rules, people don't follow it in the end. Still, like it's difficult. You can help by making this benchmark suite that alleviates some of these issues, but otherwise, there's no guarantee people follow your rules.
So on that point, there are rules in the TPCH benchmark, right, that
Yeah.
you need to be able to unplug the cable, replug it, and your data needs to be resilient to that.
Yeah.
I don't think there are a lot of commercial systems that do that. And I don't know, I certainly, don't think I know a lot of systems even that do that. I think that's the thing, right? Like, you have this space between like excessively complicated and, well, sloppy. And this is like pushing very much to one side. Like, I don't know, there are some things like, maybe you don't want to deal with overflows. You're checking like, how fast can my database go if I don't do overflows. If I can statically somehow prove that there are not going to be any.
Sure, that's also dealing with overflows. It's handling overflows. It's overflow detection, prevention instead of detection, but it's still handling overflows.
True, but I like to do in a sentence in my evaluation. I don't
Sure.
need to implement anything.
No, sure, but then you do deal with it in some way, right? So.
All right. Okay, that makes it a lot easier to affiliation.
Yeah. Well, if you put the arguments in the paper, I think.
Actually, related to what Holger said, they do, or actually they are forced to, because since commercial runs, they are auditors, and these auditors are not your friends.
No.
So they do these things like put them all like in the middle of the run and then see
Yeah.
how it works. The problem of course is that if you write a paper,
We don't have the auditors.
So one thing which would make sense perhaps is to decouple the paper from the experiments. Like you present your good result, which is interesting, and somebody else tries to measure how this works out.
Yeah.
In reality, you have to put it through, but this would make sense in abstract sentences because then somehow more neutral just experiments.
Yeah, definitely. That's a really good point.
Hi, this is fun. A lot of stuff you're recommending strikes me as being very similar to what are considered good development practices for software development.
That's true.
So,
Of course, research prototypes don't follow those practices.
so that interesting to me that one might take some lessons from that set of practices and apply it to research.
Yeah, that's very true.
All right, thanks a lot again.